So here on page 3, we are reviewing how we write the names of acids. And all of these rules and things are mostly about the names, but we need to understand the names in order to be able to write the formulas for acids as well. The thing we do need to recognize about our formulas is that we are always going to have acid formulas start with an H+. So when we write their formulas, because these are kind of right in the middle between ionic and covalent substances, and there's still a range here, but remember, ionic and covalent isn't a black and white decision. Most of our bonds are going to have a little bit of ionic character, a little bit of covalent, but we call something ionic or covalent once it's mostly one or the other. So these are technically covalent bonds because we're going to be forming them between non-metals, but they have a great deal of ionic character. So when we write the formulas, we're actually going to be cross-dropping and reducing our charges just like we do with our ionic compound. And that +1 is never going to get written down. We never write ones in our formulas, so that actually makes our cross-dropping and reducing easier. Technically, the formula of our acid is only going to be based off of what that ion is and what its charge is. It's always going to be a negative charge, but that charge, whatever the charge of that piece, whatever's with our H, is going to be the only extra subscript we write. That number is going to come down here and be on our H after we've crossed, dropped, and reduced. So this is kind of our general format for our acid formulas. H, some numbers of H's, and then that anion piece of our acid. So why we're so focused on writing our names today and all these rules about the names is that by understanding the names for our acids, we can use that to figure out what is that anion, what is the piece, that thing with the H, and once we have that, then we can write its formula. So there are 3 main types of acids, and the first one and the simplest kind are what we call binary acids. That means that there are just 2 elements. That's what binary means. And because one of those elements is H, then that means that we just have one other single element with our H for 2 total elements. So these are the shortest, simplest formulas, and their names are always going to follow a predictable pattern. These binary ones are the ones that are going to have that word hydro at the beginning, and then we have the root element name, which here we see hydrochloric acid has chlorine in there. Over here we see that hydrosulfuric acid has sulfur in there. So hydro, that prefix hydro, then the root element's name, and then they're always going to change the end of that element's name to have ic, and then the word acid. So this is kind of the general format that all binary acid names are going to take. So when you see H with just one other element, just focus on what is that other element and put its name here in that middle part. So hydrophosphoric, hydronitric, hydrocarbonic acid, all of those are just H and that one other element. Then next, we have some non-binary acids. So these are going to be acids that have 3 or more elements in them. And because one of those elements is always H, really what we're talking about are acids that have a special group, 2 or more elements combined into a group that are bonding and connecting with that H+. And remember that all of our special groups of atoms that we deal with are on the back of our periodic table. So let's go take a look at that real quick. Pull yours out if you have it. So on the back of our periodic table, we have all of our polyatomic ions here. These are our groups that are special groups of atoms. And we have some groups that end in ate and some groups that end in ite. And there are some where they're very similar. We got chlorate and chlorite here. There's no carbonite here. It's all carbonate. But some of them we have more than one possible ending for them. And the only difference is how many oxygens are connected to that root element. So we need to look at the endings of those pieces. These can all connect with an H plus in order to form an acid. And depending on which version of that nitrogen group is connecting with our H, then we're going to name it slightly differently. So this next type that we have here are if that piece that's with my acid is one of those groups that ends in "ite," then the acid name is going to be ending with "us." Notice that we don't have hydro here. We're just jumping straight into the root element's name, and then it's going to change to having "us" instead of "ite." And then we still end the whole acid's name with the word acid. So here we have sulfurous acid, and over here nitrous acid, just taking that "ite" ending and replacing it with "us." Then if we do have one that is a polyatomic that ends in "ate," which these are pretty common, we see a lot of those on there, then that "ate" ending is going to be changing to "ic." So we still don't have any hydro at the beginning. It's just ending with "ic" acid if we have a polyatomic with our H, and that polyatomic's name normally ends with "ate. And we change it to end with "ic." So nitrate becomes nitric acid. So this is kind of the general naming rules that the general naming trends we're going to follow, kind of the fill in the blank, making an acid name. I think that can generally help people understand these differences and similarities, but trying to remember which ones are which are sometimes a little bit difficult. So my two kind of hints, my two general reminders, what we need to decide and remember is when do we use hydro and when do we use no hydro at the beginning. And the general rule, because we only use hydro on our binary compounds when it's just H and one other element, the saying that I remember is that we use hydro when there's no O. So then it's just H and our element, then it's a hydro acid. If there is some oxygens, we can call those oxy acids, but we don't put oxy in there. We don't put anything at the beginning. We just jump to the endings. So we use hydro only when there's no O in our chemical formula, our acid formula. And if we do have O's, we don't start with hydro, and then we still need to choose between "ic" and "us." And so this little saying that I've got here is "ic, I ate a humongous bite." And what that reminds us is that we're going to take our polyatomics that end in "ite" and make it "us," or remember, "us" comes from "ite," and then that our "ate" is coming from or turning into "ic" acids. So "ic" goes with "ate," "us" goes with "ite." And that, I know it's silly and random and doesn't seem to make any sense in the grand scheme of things, but it's been stuck in my head since I was in sophomore chemistry, and it helps us remember how to end our acid names when it's not a binary hydro acid. So let's go ahead and use some of that. Actually, I'll leave that up there while we do these first few examples, and then I'll scroll down to finish the rest with you, with those not being visible. So as we get started here, as we're looking at this first row, if I'm telling you that I'm going to be putting this I-1 with my acid, and remember that H is an H+1 there, if I'm combining that with I-1, then I don't even really need to cross-drop reduce here. +1 and -1 are going to cancel each other out. So our acid formula here is just going to be HI. Now if I'm trying to name that, first thing I need to ask myself is this a binary acid? Am I going to need to put hydro at the beginning? And it is. I've just got H and I. So my name is going to start with hydro. And then I need to focus on what is the name for I? That's iodine. So we're going to take iodine and then change that last ending. The iodine changes to having an ic ending. So that's going to be iodic acid. hydroiodic acid to be precise. As we continue down on the next row, really what I'm focused on is trying to find the name for that H3PO4. But in order to figure out the name, I need to first focus on what is the name of that thing that's with my H. And if I look on the back of my polyatomic list, then that is PO4 negative 3, and we call that phosphate. And as soon as I see that that is phosphate, then I know that that is not going to need hydro at the beginning. We've got some O's in our formula, so I do not start with hydro when I've got any O's. So I'm just going to start my name with that phosphate, but that 8 ending is going to change to ic, so that's going to be phosphic acid. Full credit, 100% correct, at least at this level of chemistry. Now, I don't expect you to be able to anticipate this, and I am going to put it back the way that it is, but technically, the way that chemists name this is they call it phosphoric acid. Why they add an extra syllable there? I know it's from phosphorus, but why do they add an extra syllable that they didn't keep in phosphate? I mean, no one really wants to call it phosphorate. That sounds weird, but honestly, I think that some old chemists back in the day decided that phosphic acid sounded weird, and so we just wanted to add an extra syllable there to make it sound better. And I don't expect you to be able to anticipate, predict, or memorize when you need an extra syllable or not. So as long as you're following our general naming rules, find the root name, change the 8 to ic, add the word acid, I will give you full credit for this here. What you need to be mindful of is you're never going to see me or any other chemist write that out. So if I tell you later on in this unit that phosphoric acid is reacting with sodium hydroxide, I need you to be able to recognize phosphoric, even though it's not phosphic, does come from phosphate and has phosphate in it, and be able to write that formula from the word phosphoric. But I am not going to expect you to remember that or count off if you just drop those 2 little letters. Everything about this name is perfectly fine for now. We'll work on it as we continue getting into higher and higher levels of chemistry. And the more you use these names and see them and read them and say them, the more you're going to get used to some of those weird little kind of twists. So here we're given an ion again that we want to put into a formula and find the name of. And the formula is always the easy part, especially if, just like we did before, you have C2H3O2, and that has a -1 charge. Well, when we put that in acid, that -1 and +1 are just canceling out. So I just need an H up front with this C2H3O2 thing, and that's my acid's formula. Now, if I'm writing a name from it, then I need to know the name of that crazy thing, and that is acetate. And so just like before, I'm seeing that's ending with 8. I'm just going to change that 8 to ic and then add the word acid. So this is actually acetic acid. You might think it's acetic acid, but once again, they just kind of changed the way that sounded a little bit to make it roll off the tongue a little bit better. So acetic acid it is. Now let's look at the rest of that table and examples. All right, so our 4th row is asking us to find the name of this acid, and so we need to think about what the name of that NO3 thing is, and it does have a -1 charge according to the back of our periodic table, which also tells us that this is nitrate. And just like our other 8 acids that we've been seeing and practicing, and there sure do seem to be a lot of them, that 8 turns to ic, so this is nitric acid. The next row, we're writing a formula and a name. If we put that SO4 -2 with my H+, this is the first time my charges are not going to cancel out automatically, so we are going to have to cross drop reduce and bring that 2 over. Remember, the 1 isn't really going to get written, so it's not really needing to go anywhere, even though it does technically cross drop reduce to finish that out. But in the long run, our answer is H2SO4. And as we're thinking about the name for this acid, the name for that group is sulfate. So once again, 8 is turning to ic, and this is going to be, well, it's going to seem like it's sulfic acid, but this is another one of those where they added a random syllable and actually ends up being the entire name of that root element. But evidently sulfuric acid sounded better to them, and that is the common name for our H2SO4. Now this next row is actually a really important one to practice and pay attention to, because what we're going to need to do most of the time is be taking a name and turning it into a formula so we can write a reaction or figure out what's going on with the chemistry of that formula. So this is a skill we need to be able to practice, is use a name to figure out what is with our H so that we can write its formula. So if we're looking at chloric acid, I know that this is going to be chlorine in it because it's got that chlor ending. And I kind of need to be asking myself, is it just chlorine in my acid, or is that one of those chlorine and oxygen groups? And I can tell that this is going to have some oxygen group and be a special group from the back of my periodic table because it doesn't have hydro here. We would call it hydrochloric acid if there were no O's in my formula, if it was just H with that Cl. But because this isn't a hydro acid, then that means that I do have some oxygens in a special group from the back of my periodic table. So I'm going to start flipping my periodic table over, and because this is chloric acid, then that must have been chlorate that was in my acid. And chlorate is ClO3 with a -1 charge. So that's what I'm going to be combining, my ClO3 -1 with my H + 1, which means my formula for chloric acid is just HClO3. This next name that we're looking at is a hydroacid, hydrobromic acid. So that hydro tells me there's no O's in this. This is just H and one other element. And because it's hydrobromic acid, then that is going to be bromine, which does have a -1 charge. So if we put that with our H + 1 instead of our other ion, Br's -1, that +1 are canceling out, and we end up with HBr as our formula. Back to writing a name here, I need to ask myself what the name of this Cr2O7 thing is, and be careful because there's another ion that looks a lot like it. That is dichromate. And I didn't add the di to that. That is just read straight off the back of our periodic table. So just like nitrate and sulfate up there, any polyatomic that ends in 8, all we do to write its name is change that 8 to an ic. So this is dichromic, and then the word acid. Hydrofluoric acid. Hydro means there's no O's. It's just H and one other element, and that element is apparently fluorine, F. And F does have a -1 charge, so hopefully I was about to say, it's just like that previous formula we wrote, and I was looking up here, still way too much. But yes, if that is F -1, then that is going to cancel straight out, and we don't have to do anything else with that formula. We've got a lot of these really simple acid formulas, so even though the names can seem complicated and weird and confusing, when in doubt, just stick an H on that element that you know is there, and it's at least possibly correct. So here, H2SO3, we want to write its name, so I need to think about the name of SO3, and that is sulfite. And so we are going to take that ite ending and change it to us. So this is sulfus or sulfurous acid. Making sure it ends with us at the very least, and then the word acid. And last but not least, we're trying to write a name and a formula for an acid with that CO3 -2 charge. Because that charge is not a -1, it is going to be crossing over onto that H. So this is going to become H2CO3. And the name for CO3 is carbonate. And so if that is ending with ate, then I'm going to change it to ic. So that becomes carbonic acid. So there are a few naming practice problems and formula writing practice problems at the bottom of page 5. Down here, that last chunk of properties, or of acid and base stuff, and most of these are acids, but these last 3 are actually bases. So everything we just talked about is going to apply to those first 2 rows, all of those formulas. And I think we've actually seen all of those before, but practice finding their names all on your own, and then you can check back to that page 3 page to double check and make sure it agrees with those names we've already found. There's not really that many acids to name and write formulas for, so you are going to see these repetitively over and over again. So hopefully that helps them stick. A quick word about our base formulas. Our bases, at least the common ones that we're going to be dealing with for the most part, are generally going to have that OH group at the end, and all we call that's name is hydroxide. So here where I have an Na with that hydroxide group, our name for this compound is sodium, because that's what Na is, hydroxide. This is just a plain old ionic compound, first name, last name, and when we have a special group like that hydroxide at the end, we don't even change the ending. So that is the full name for NaOH. And here, when I'm given the name of an acid and I have to write its formula, just like any other ionic compound, we're going to have to find the symbols of those pieces and their charges. Barium's in the second column, so it has a +2 charge. OH is a special group, so the back of the periodic table tells me it's a -1. And because they don't match and cancel out, I am going to have to cross that over, bring that down, and my formula is going to be BaOH2. In a similar way to our acid formulas, because that piece, the thing that makes us a base, has OH, and it always has a -1 on it, the only thing that is ever going to change about our base formulas is what is that thing that's with our hydroxide, and what is its charge, because that charge is going to always end up coming over and crossing onto that OH. OH's -1 is never going to get written here, so it's always just Ba or something, OH something, all together. Now, this last one, NH3, is kind of a weird thing. If you had written it H3N, technically that's hydronitric acid, but we didn't write the H's at the front, so the way this is bonded is actually not going to act like an acid. Even though it has H's in it, it doesn't mean that it's an acid. So like I referenced a moment ago, this is actually a base. It's a weak base, and its common name is ammonia. So we might be seeing and hearing about ammonia on and off throughout this unit. But if I ever need you to be able to write this formula, then I will write it out in its true covalent naming structure, which is nitrogen trihydride. Just nitrogen and 3 hydrogens. So if I call it that, I expect you to be able to recognize that and write its name, and then evidently it might be going around acting like a base or something. But the common name for that is ammonia, and you'll probably be hearing more about ammonia later.